Welcome to today's webinar, Modeling Combustion in Liquid Rocket Engines, brought to you by Convergent Science. Thank you for joining us today for the 9th installment of the 2024 Converge webinar series. My name is Mattia Suris, and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and learn about the tools that Converge CFD software offers to model liquid rockets. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, David Rowinski. David leads the new application support team at Convergent Science in the Madison office, where he assists customers with CFD problems across a variety of applications. He earned a PhD in mechanical engineering from Cornell University. During today's webinar, if you have a question for David or the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to David. Thank you all.
All right, well, thank you, Mattia, very much for that introduction. As Mattia mentioned, my name is David Rowinski, and it's a privilege to be here today with everyone to present our webinar on modeling liquid rocket engines with CONVERGE CFD. So in this approximately 1 hour webinar, we're going to talk about the capabilities offered by CONVERGE, specifically for the application aimed toward the end goal of modeling combustion in liquid rocket engines. And we'll focus the webinar mostly on the effects of the equations of state, combustion, and turbulence, as well as highlighting the unique features offered by CONVERGE, which make it a great fit for these challenging problems. Toward the end, we'll give a very brief workflow demonstration of a multi-element combustor and show the users what's involved with a practical type of case setup so that you can get some idea after you've seen all of the studies what it involves to use yourself. And then at the very end, we'll touch on a couple other related application areas, just very briefly, but the bulk of the webinar will involve this end goal of what does it take to model liquid rocket combustors. And just as a very brief intro for anybody who's not familiar, we'll go over what is the basics of a rocket engine so we can frame our discussion. In a rocket engine, we have the characteristic that the fuel and the oxidizer are stored entirely on board, so it carries with it all of the propellants. The fuel and oxidizer are then mixed and burned in a combustion chamber, and those combustion products are accelerated out through the nozzle to produce the thrust. That's the very basic purpose, and there's a really basic classification of these rocket engines into two broad categories of the solid type of combustors, in which the fuel and oxidizer are in a premixed bindered grain, which is then burned, in contrast to a liquid rocket, which is going to be the subject of today's discussion, where the liquid and the fuel and the oxidizer are stored in liquid form and then pumped and injected into the combustion chamber, where they are subsequently mixed and burned. Now, the key flow processes in rocket engines for which computational fluid dynamics type of analysis is useful includes a variety of real problems, including the safe storage of the fuel and the oxidizer, the flow of the fuel and the oxidizer through all of the components, and then the ignition, combustion control, stabilization, and maximization of combustion efficiency, which is one of the main points that we'll be looking at in this webinar. For solid and hybrid type rockets, there's additional complexity involving the grain shape. And for liquid rocket types, the fuel and oxidizer composition, flow rate, and all of the upstream flow dynamics are very important when considering the fluid dynamics type of modeling. And then lastly, although it's not a main objective of this particular webinar, of particular interest in the practical design are issues related to the heat transfer, the cooling of components, as well as the nozzle flow. To frame our discussion and the kind of environment we're going to be looking at these in this webinar, I'd like to give everybody a sense of appreciation for how extreme the environment inside a liquid rocket combustor would be. So these flows typically involve very high speeds at some point or another, with a large range in possible Mach numbers, as well as highly turbulent flows characterizing at least part of the domain with very large range in Reynolds numbers. In terms of the reacting flows, the fuel and oxidizer combinations could involve tens to hundreds of species. A large range in the heat transfer can be encountered in these environments. But most importantly, and the major focus of today's discussion is going to be on the wide range of the phase space accessed in these type of in this type of environment. So we'll start on the injection side, where the fuel and or oxidizer may be in the form of very low temperature cryogens, anywhere between 20 to 100 Kelvin, whereas the products of the combustion can yield extremely high temperatures, characteristic of combustion or equilibrium compositions. And looking at the pressure, we have a similar very extreme range in the pressure, going from near vacuum at the exhaust to extremely high pressures near the injection and in the combustion chamber itself. So a really interesting contrast is to take a look at the extreme temperatures we have at the throat or within the combustion chamber, in contrast to the temperatures near the injection site, which are so low that ice may form. So this is very characteristic of the type of problem that we want to demonstrate our different solution approaches to, and help the users understand what kind of advantages Converge can offer for these type of extreme environments. All right, and then we have a very brief kind of value statement on why Converge is a great fit for these applications. And although Converge has a really large number of amazing features, there's three that are really highlighted in this application area. The first is no user meshing. So the ability to bring in any geometry of an arbitrary complexity and have it be easily run through a flow analysis is extremely useful when the practical devices we're dealing with often involve very complex geometries. And those geometries are very strongly related to the dynamics of the flow in many cases. Secondly, the automated and adaptive meshing approach is really key for modeling these cases with enough accuracy so that you're resolving all of the important length and time scales, but enough efficiency so that you're not wasting cost where it impacts your end outputs as much. So this is, again, one of the unique features that's offered by Converge, and extremely advantageous for these kind of environments where you could have very, very large gradients through space and very large variations in time. And Converge will take care of all of this for you with a really accurate and efficient mesh, which is easy to set up. And then lastly, and what will be the focus of most of our talk today, is the sophisticated suite of models offered by Converge, which are relevant to this broad category of multi-phase turbulent reacting flows, and that's what we're going to be discussing mostly today. A brief overview of what type of equations of state or other fluid models are offered by CONVERGE is what we'll go over next. At the very basic level, we do offer ideal gas equations of state, which for some combustion models, or rather some modeling some combustors could be, a very efficient approach. It's by far the least expensive, and with temperatures as high as they are, especially for lower pressures, ideal gas may be a good solution for some practical combustors. On the other hand, the next level of complexity offered by CONVERGE is in the category of the cubic equations of state. For example, the Peng-Robinson or Schwabe-Redlich-Kwong equations of state. An alternate option, though, offered by CONVERGE is the tabulated equation of state, which has kind of three flavors, one being the single component tabulated equation of state, which is a fairly simple two-dimensional table that can be generated in a pre-processing step, so you don't really need to worry about how expensive the equation of state is to evaluate. And then two additional options for cases involving multiple components and mixing, one including the ideal mixing rules, and another one including an additional tabulated dimension, which will account for more accurate mixing properties. And we'll talk about these options later in the slide. As far as modeling the multiphases go, in addition to the detailed equations of state, CONVERGE offers volume of fluid approaches, which can be coupled with compressible or incompressible models of the fluid. And then lastly, there's a wide suite of Lagrangian spray models offered by CONVERGE, the most complicated of which can be coupled with your continuous phase model through ELSA. CONVERGE also offers a very wide range of combustion models, although the main focus of this talk is going to highlight detailed chemistry, which we call SAGE. And this is a great model because it's applicable across all modes of combustion. It's very accurate and easy for users to set up. With our adaptive zoning, it's actually pretty affordable too. On the other hand, we do have a wide variety of simplified models which are applicable to select modes of combustion, including FGM and RIF for a flamelet-based type of non-premixed combustion model, ECFM3Z, applicable to some premixed and non-premixed cases, as well as eddy dissipation model on the mixing timescale type of problems, and G equation primarily for premixed combustion problems. And there's a suite of submodels that are applicable to most of these combustion models, including models for NOx, and some of which may be important to modeling practical combustors. In addition to all of these CFD combustion models, CONVERGE also offers a variety of tools for simplified combustion analyses, one of which is the isentropic nozzle calculator, which is really useful for these applications in order to get a good initial condition. In the category of turbulence models, CONVERGE offers three main types, first of which is RANS, Reynolds average Navier-Stokes equations, and there's a wide variety of those models offered here. The large eddy simulation is a great offering by CONVERGE, which is in particularly useful for these combustion analyses where we're looking at unsteady effects and instability prediction. And then finally, the detached eddy simulation offers a combination of the RANS model for accuracy near the wall and large eddy simulation in the far field. So all of these models are offered by CONVERGE and will demonstrate mostly the large eddy simulation and some RANS models in the context of the combustors that we'll look at. Now, while the main end goal of the benchmarks that we'll show today are aimed toward modeling liquid rocket combustion, in this webinar, we're going to take you step by step through 3 layers of complexity, all of which are prerequisites to being able to model multi-species, turbulent combustion kind of problems across a wide range of phase space. So we're going to go through in this webinar, this slide kind of highlights the main overview of what we're going to be looking at, a progression of demonstration cases starting from the simplest and moving toward the complex. And in the very first one, we'll demonstrate the use of CONVERGE for modeling supercritical flows of single components. And after that, we'll go to our next layer of complexity where we talk about mixing dynamics at supercritical conditions for more than one component. And finally, after we've demonstrated the features and the model setups necessary to do these previous 2 problems, we'll talk about adding combustion into the mix with first ideal gas type of conditions or conditions that don't involve such low temperatures. And then after that, talk about the supercritical and subcritical combustion type of models available through CONVERGE. So just about all of these cases involve super or subcritical flows. So we have wide range in the accessed phase space. The last 4 all involve mixing, and then the final 3 involve combustion. So this is our progression, and this is the kind of the roadmap for this webinar of what steps we'll take to show you how to reach this end goal of modeling the multi-phase, multi-component reacting mixtures with CONVERGE. All right, and we'll get started with that right away by looking at our very first category of cases, the simplest ones that we'll look at today, where we look at the use of CONVERGE in modeling supercritical flow and subcritical flow of single components. And there's a variety of test cases that we use to assess CONVERGE's capabilities in this area. One of them being the well-studied RCM1 cryogenic nitrogen injection case. This case involves a single cylindrical injection of low temperature nitrogen, and it's particularly designed to mimic conditions encountered in liquid rocket combustors. So the environment pressure that's being injected into ranges between 4 to 6 megapascal, which is just over the critical pressure of the nitrogen. So all of these cases will involve the supercritical injection. So for a single component case at these conditions, what is so hard about the problem? And the main complexity in the problem involves the variation in the density and the other thermodynamic properties, mostly as functions of temperature. So over the range of temperatures that are injected into, we have a potentially very large change in density, and similarly changes in the thermodynamic properties. For example, the specific heat ratio, which is shown in this bottom plot. So similarly, a lot of the thermodynamic variables have very strong change throughout the conditions encountered in this relatively simple test case. There's 2 primary approaches applicable in CONVERGE for this type of problem. The first being the analytical cubic equations of state. And in this particular model, something new added for CONVERGE 4 is the Chung correlation for the transport properties. We also offer a constant pressure tabulation, which can be used to specify the transport properties at a particular pressure or over a range of pressures. It's important to note that with this model, we still do require discrete tables for the departure functions. And one of the new capabilities offered by CONVERGE 4.0 is the ability for users to have a fine-grained control over those resolutions so that we can get them fine enough to resolve these kind of changes encountered throughout the conditions. Now, the second possible approach in CONVERGE is to use the tabulated fluid properties approach. In this approach, we generate a table ahead of time through another tool, for example, the open source utility CoolProp, where we can use a higher accuracy equation of state and also retrieve the transport properties as well as the thermodynamic properties for these highly accurate and validated equations of state. And both of these approaches are available in CONVERGE. Now, one of the main capabilities that's offered by CONVERGE 4.0 is the real gas pressure velocity coupling. In this approach, we use the derivative expressions from the actual equations of state to solve our transport equations within each time step. And this allows us to simulate over a wide range of changes in our density and thermal properties, no matter how they deviate from the ideal gas properties. So like I mentioned, in addition to the RCM1 case, we have validated against a number of cases. And when looking at the actual data for comparison, there's always some uncertainty due to the unknown actual temperature around injection. So while we do demonstrate results that look very similar to what's measured, that's not really the main point of this demonstration. The main point is rather that the solver runs robustly through this extreme range of conditions, including one of the cases from the AFRL injection case, which is slightly different from the RCM1 case. And in this case, it's even more challenging because the pressure is lower than what's encountered in the RCM1 case. So instead of 4 megapascal, the lowest pressure is about 3.5 megapascal, which is much closer to the critical pressure of the nitrogen. So as you go lower and lower in pressure, the variation in the properties becomes larger and larger towards the critical point, and it's a better and better test case for the solver's robustness. So we've demonstrated the robust functionality of CONVERGE 4.0 across this very wide range in conditions. And then next you may be asking what happens as the pressure gets even lower than that. And as the pressure reduces to beyond the critical pressure of that single component, we enter the subcritical regime where the injection dynamics could change significantly from the supercritical conditions. And for the subcritical injection, there are 3 primary options available with CONVERGE 4.0. The first being the volume of fluid method, which is pretty robustly tested out through a lot of different test cases. The disadvantage of the volume of fluid method is that the equation of state is somewhat simplified from the other approaches. So in this case, we're limited to a compressible liquid model. So we sacrifice some of the thermodynamic accuracy because of that. However, it's a very relatively fast method, and a lot of times for your known conditions, it's quite a good approximation for that equation of state. Now, the second approach is an enthalpy-based tabulated equation of state. With the enthalpy-based approach, instead of a pressure temperature table, we use a pressure enthalpy table. And this has the advantage of being able to fully parameterize the phase space from subcritical to supercritical conditions, which gives us the option to include the 2-phase region in the simulation. So this is a new feature for CONVERGE 4.0 and offers an option to perform these subcritical injection cases with a very highly accurate equation of state, which, if nothing else, is extremely useful in order to compare the effects of the volume of fluid method. And that's what we're going to do in the next slide. A third option, particularly applicable to atomizing sprays, is the Lagrangian or the fully coupled ELSA approach, which we'll talk about later. So in this example, we've looked at both two-dimensional mixing layers as well as 3D axial injectors over the range of conditions studied in the AFRL experiments. And in these conditions, the reduced pressure, which is the pressure divided by the critical pressure, goes from the extreme high end of 2.7, where we're supercritical, all the way down to 0.23, where we're in a subcritical injection regime. Converge with the enthalpy-based table runs robustly through this wide range in the pressures. And when we compare it to the other multi-phase approach, the volume of fluid method, which is shown in this video on the bottom left, the results are, in terms of the core length, are actually pretty similar between the two of them. Where you do see a little more difference is when you look at the mixing thermodynamic behavior. You can see because of the different equation of state that's implied by the VOF model, we have slightly different mixture temperatures as a function of the mixture fraction. So in terms of the model complexity and the cost, it's very similar, but as we'll discuss, each approach has certain advantages when we look at more complicated problems. So here's another demonstration of the tabulated fluid properties versus the volume of fluid with a compressible liquid equation of state for a slightly different condition. And this condition was chosen so that there's more air associated with the simplified equation of state for the VOF model. And in this demonstration, we showed VOF model is, in addition to the equation of state being different, has the ability to include the non-equilibrium effects in the phase change, which is why you see these density versus temperature profiles deviate, whereas the tabulated equation of state assumes equilibrium properties at all temperatures and pressures. The volume of fluid model does allow the timescale to affect the phase change rate, so you get some difference there. What we don't really know is which is more accurate, the non-equilibrium effects together with the non-equilibrium effects together with the simplified equation of state, or the more accurate equation of state with equilibrium phase change. Okay, so having looked at the single component test cases at both sub and supercritical conditions, we'll move on to the next layer of complexity, and this is in modeling the supercritical mixing dynamics. The main test case we'll use to demonstrate the features offered by CONVERGE is in a hydrogen-oxygen mixing layer, although we will demonstrate the applicability in some other cases as well. And the very first thing I'd like to demonstrate and hope that you get some appreciation for is how complex the additional element of the mixing can make the problem statement. So as soon as we introduce another component, we can have a possibly very wide range in properties and a very large deviation from the behavior of those single components. In the case of a multi-component mixture, the thermodynamic state is parameterized by the pressure, the temperature, and the mass fractions. And the mixture properties, as this diagram from another work does a really great job to show, may be very different from the properties of the pure components. For example, as shown in this picture over here, we have a mixture of dodecane and nitrogen, and although the pure components' critical points are exceeded in all of the pure stream conditions, the critical points of the mixture are extremely different, such that we get two-phase behavior in this type of mixture. And to demonstrate this, we'll use 3 different cases to show CONVERGE's different models applicable. The first being the 2D mixing layer of cryogenic oxygen and hydrogen. Then we'll also show a coaxial jet of nitrogen and hydrogen. And lastly, a diesel-like injection scenario modeled with the same approaches. Okay, so in the two-dimensional mixing layer case, this is a numerical benchmark which has been looked at with a couple different solvers. CONVERGE has been compared pretty extensively to all the other results, and for similar setups can yield similar results. The main point, however, is to show what other options are available in CONVERGE for modeling such a problem. In this problem, as shown in the figure in the bottom left, we look at the temperature versus the mole fraction of the hydrogen, and there are 2 equations of state shown in this figure. The first being the standard cubic equation of state, where we only look at the largest root, which is the common approach mostly used when the cubic equation of state is used. But that's contrasted to a more detailed, the same equation of state, but with a vapor-liquid equilibrium computed for all of the points which fall into the multiphase part of the phase space. So this is demonstrated through the third option I mentioned for modeling mixing with a tabulated equation of state. This was developed together with our collaborators at IFP, and it involves performing a tabulation before the simulation, where we use the pressure, the temperature, and the mixture fraction to determine the properties, including the density, the energy, and all of the transport properties. We can compare this to 2 different approaches, one of them being the standard cubic equation of state with a single root, and then the volume of fluid method, which we didn't show here, but we showed previously. And the main thing to appreciate is that with the second model shown here, the tabulated real fluid model, we're able to, in this type of simulation, predict the existence of the two-phase region between the hydrogen and the oxygen. Although the pressure is far above the critical pressure of both components, we do predict a existence of a two-phase region with this approach. So as shown by this red area here, this indicates the region of the physical space where we have two-phase behavior, and this allows us to add complementary surface tension forces wherever the interface is present. Meanwhile, within each of the cells, the homogeneous approach is used, so any cell falling within the two-phase region has a homogeneous composition composed of the sum of the liquid and the vapor properties. This model also allows us to consider the differential effects of having component compositions change within the two-phase region, which is a capability that neither of these other approaches, the standard cubic equation of state or the volume of fluid approach, can offer. So for cases that are very sensitive to the mixture density and or the mixture temperature, this is a really useful approach that is a great capability of CONVERGE 4.0. A second test case to examine the multi-phase, multi-component mixing is the coaxial mixing jet of hydrogen and nitrogen, again at cryogenic conditions. There's an annular inlet of hydrogen. which encloses a central inlet of cold nitrogen. These are injected into an environment slightly above the critical pressure of the nitrogen. So in this case as well, we do get two-phase behavior, and the CONVERGE model is roughly compared to the density measured experimentally, but again, more importantly, showing the solver running robustly and with a thermodynamically consistent model across this wide range of the phase space. Now, the last problem we'll demonstrate for the multi-phase, multi-component mixtures is a very different application, but with very similar conditions, and namely that's the spray A conditions involving the injection of high pressure N-heptane into nitrogen. And the purpose of doing this is to show that the conditions encountered within the liquid rocket combustors are similarly encountered in other applications, and the models being used here do a great job to offer additional levels at which we can look at the model complexity. So in this approach, we compared the standard Pang-Robinson equation of state with and without the vapor-liquid equilibrium calculation. And you can see again here by this plot showing the mixture temperature versus the mixture fraction that we do have a considerable part of the mixing space occupying the two-phase region. And this approach offered by CONVERGE, together with our collaborators at IFP, allows us to look in detail at that two-phase region and understand how the properties encountered in that two-phase region affect the end outputs that we're interested in. If we compare the result here from two other simulations, we can see two main takeaways. One, that other simulations that encounter that consider the vapor liquid equilibrium part of the phase space give a really similar result in terms of the mixture temperature as a function of the mole fraction, whereas models that don't consider this effect may have a much different scatter and phase space. In other words, the mixture temperature could be very different if the equation of state is different. Now, in addition to this, there's a couple other approaches offered by CONVERGE which can be really useful depending on your end goal. This demonstration here shows the volume of fluid approach applied to a very similar problem. And with this approach, although we've sacrificed some of the accuracy of the equation of state, if the end outputs we're interested in don't depend too much on that, for example, if we're more concerned about the acoustic propagation throughout the domain, then the volume of fluid approach offers a very computationally efficient and robust method for looking at those types of conditions. On the other hand, incompressible models are also available in CONVERGE if users are more interested in looking for, especially for subcritical injection at the interface that occurs between the two phases. So with the incompressible approach, we can get a much higher accuracy prediction of the interface, although again, here we've sacrificed even more of the equation of state by using an incompressible model. So depending on the purpose of your studies and the conditions that you're working at, any of these three models may be of more interest to you. On the other hand, if phase change is of high importance in your case, the volume of fluid method, as shown in this gasoline injection case, offers a lot of advantages in terms of being able to predict the non-equilibrium phase change in a very similar way to what we showed in the single component cases. Okay, so now that we've looked at both the pure component behavior at sub and supercritical conditions, as well as the mixture behavior, we're ready to throw in the next layer of complexity into our models, that being the reaction element. So the next three types of cases we'll look at will involve the gaseous conditions, the supercritical conditions, and lastly, the subcritical conditions. This case shown over here is the Penn State combustor. Although it's at a high pressure of 5 megapascal, the real gas effects aren't as important here because the injected quantities are coming off a pre-burner. So they're elevated in temperature. They're not at the cryogenic type of state that we have in the other problems. And in this problem, the main objective that we'd like to show is how to set up CONVERGE's mesh strategy and how to get a complicated case like this up to steady state in a reasonable amount of time. In this case, we also have the complexity that the chamber pressure is a function of the flow through the nozzle. So we don't impose the chamber pressure, rather it's predicted by a combination of the flow properties at the exit as well as the overall combustion efficiency. So the process we use is a three-step process involving a calculation without the nozzle and an imposed pressure based on equilibrium combustion. From that, we map that to a coarse grid using CONVERGE's mapping feature. And after that, we activate AMR to get a higher accuracy solution once all of those have reached a steady enough state. And with this kind of approach, we solve all of the other combustion-related problems that we'll show over here. So the main purpose of this case isn't so much to demonstrate the accuracy, although the chamber pressure reached is approximately that 5 megapascal, which is measured, but rather it's to show the approach in getting these complicated cases up to steady state in a reasonable amount of time. Now, from this gaseous hydrogen case, we'll look at an additional layer of complexity, which is making the fuel composition more complicated. So we'll look at a methane oxygen case at a slightly lower pressure of 20 bar, but again with higher temperature inlets so that we don't have the complexity of the cold temperatures that we'll have in the next cases. And the purpose of this test case is to show the advantages and disadvantages of the different combustion models offered by CONVERGE. And this is a great test case because unlike a lot of the others, it has a pretty large amount of optical data, important in understanding where the flame is located. So like this picture shows on the bottom right, the OH concentration, which is a general indicator of where the flame is located, with the flamelet generated manifold solution, which is shown in the very bottom right. We get flames that are anchored closer to the post tip, whereas with sage, we get more of a lifted flame, which is also a function of the grid resolution around this part of the flow, and it can be something that we can validate to the experimental data. So if we look to see where the flame is actually anchored according to the time averaged images, we get something that's kind of in between what we get from SAGE and FGM. The advantage of FGM in this case, however, because the fuel is more complicated, is a little more pronounced than it would be for a hydrogen type of case. And then a very similar approach has been used by one of our university collaborators at North Carolina State University, where they performed a similar analysis, but on a challenging flow configuration that involved the prediction of the acoustics within the chamber. And very interestingly, the compressibility from the model, as well as the interaction with the reaction rate, predicted a very good match in the internal acoustics of the combustion chamber. So it's an application of a similar approach that was shown in the test case before, but for a test case that has more variation in pressure throughout the chamber and could be experimentally validated. Now, the next layer of complexity to further add to these cases is the supercritical conditions where the fuel or the oxidizer come in at a low temperature. And in these cases, now we need to be a lot more conscious of our equation of state and or other fluid models used in the study. And in this demonstration of the RCM3 case, where we have a chamber pressure of about 6 MPa and a oxygen injection temperature of around 85 Kelvin, we need to be much more accurate in our thermodynamics as well as our transport properties so that we have the right properties of our fuel coming in. And the major thing to look at is the prediction of both the core length of our oxygen, which is in the center, as well as the flame shape. So for this particular test case, we looked at a couple different scenarios. The first ones up here compared to another work are done with CONVERGE's new two-dimensional axisymmetric solver for both a lower flow rate of hydrogen on the bottom, the C60 case, and a higher flow rate of hydrogen on the top, the A60 case, and contrasted to a full three-dimensional LES simulation of this particular case, which is shown on the bottom. So the 2D solution was used to initialize the full 3D case. And again, in all of these cases, the same approach used in that first combustion benchmark we showed were used to get the simulations up to a stable burning state in a relatively small amount of user time. An additional case that can be contrasted to the RCM3 case is the NASA single element injection case. And the nice thing about this one are twofold. First, that it looks at a wide range in the chamber pressure, spanning sub to supercritical conditions, as well as the fact that the chamber is relatively small. So the flow through time is small, and it allows a modeler to quickly assess the ability of the model to yield a stable burning flame within a combustor that includes the throat and all of the potentially high velocity at the exit of the throat. So unlike the RCM3 cases, this simulation was used with the actual nozzle in there so that the chamber pressure could be predicted from the model itself. And in this case, we compared and contrasted a variety of approaches for the equation of state. The first, as shown with the blue line, is the chamber pressure from the ideal gas equation of state. And the following lines in the lighter blue through orange are all with more complex equations of state, including the orange line, which is the tabulated fluid properties approach for the multi-component mixtures, which is a new capability in 4.0 to be coupled with combustion. And this allows us to make sure we have the pure stream properties with very high accuracy. So for example, if there are any instabilities related to the flow upstream of the oxygen, we want to make sure that we have the right compressibility factor, speed of sound, etc. And this approach allows us to do that. In terms of the bulk comparison, the behavior of all the models is very similar, with the exception of the ideal gas model, which over-predicted the core length, over-predicted the flame length, and under-predicted the combustion efficiency. But for all of the non-ideal gas models, the behavior is similar. As we go to lower and lower pressures, we'll enter the subcritical regime for the injected components, and the RCM2 benchmark at 10 bar is a slightly more challenging case than the RCM3 case because of that lower pressure and because of the effects of that lower pressure on the injection characteristics. So in this video on the bottom left, we demonstrate the volume of fluid approach together with the Schwab-Redlich-Kwong cubic equation of state in the gas phase. And we compare and contrast that to a pure Lagrangian approach where the oxygen inlet is treated with an model similar to what would be used for an atomizing spray injection. And the very interesting thing about this comparison is that both models yield a similar averaged flame shape for the conditions, but we did find that the volume of fluid model allowed us to run with slightly more efficiency. These run times were slightly faster, and there was some difference about how the flame was anchored in both of the cases. One of the great things about CONVERGE is that the model variation with time is very easy to include. For these type of injection conditions, the flame is often initialized through a torch igniter or other similar injection method. And in the RCM2 case, we demonstrated how a user could set up a torch ignition model and leverage CONVERGE's adaptive mesh refinement and all of the same equations of state with a time-accurate model. And the main advantage being that because the behavior of the flow changes so much in both time and space, that adaptive mesh refinement is really critical in having a robust, efficient solution methodology. The last test case we'll show is the multi-element combustor of the BKD case studied at DLR. And in terms of the setup, and the conditions, it's actually quite similar to the RCM3 case, with the main difference that it involves a large number of injection elements, in this case 42. A very similar approach was used in the CONVERGE model for the RCM3 case, and this case here, with the main exception that the number of cells per element is slightly lower in this case. And the same solution initialization strategy was used in this case, along with a very similar AMR strategy for the other cases that we looked at. Again, mostly prioritizing the mesh around the high temperature gradients encountered to resolve the reaction zone with as much resolution as affordable. And the main output for this run is first to check that the initialization strategy to get a stable reacting flow in a reasonable time worked, and it did. Compared to our other cases, a very similar result was encountered in terms of how long it took the simulation to reach the stable pressure. And then secondly, to look to see that the main chamber pressure was predicted with reasonable accuracy. And in this case, a chamber pressure of about 8 megapascal was achieved. The same AMR strategy was leveraged in order to efficiently balance the cost and the accuracy. Now, at the very end of the demonstration on the use of CONVERGE applied to some different liquid rocket combustor cases, we'll show very briefly how the workflow looks for getting a simulation of a practical geometry up and running in an efficient amount of time. This is one of the great capabilities offered by CONVERGE that's useful for practical applications. In this case, we have a simplified and aligned model for 11 solid parts, including 7 swirl elements. We form the fluid volume simply by uniting those, and those all come into CONVERGE as the input, adding the grid control with a combination of the fixed embedding, in other words, mesh resolution based on predefined areas, usually a result of the geometry itself, as well as the adaptive mesh refinement for resolution of both the mixing and the reaction is used, and the chief outputs of the pressure and the related heat release rate are examined to see these reach a steady state within a reasonable time. The user does need to be somewhat cautious of how the simulation evolves over time so that no unfavorable regions of the phase space are accessed throughout those transients. Now, we focus most of this talk, and we're just about done here, on the calculation of the internal combustion flow within the liquid rocket combustor itself. However, there's a lot of very similar, what we call adjacent application areas where CONVERGE offers a lot of advantage. The first is film cooling, shown over here. Additionally, RDEs and other type of motors, shown over here. Propellant storage is a great application for CONVERGE, whether you're doing a fluid structure interaction problem for flexible bladders, or whether you're doing the tank leakage itself. Valves involving fluid structure interaction are a great application for CONVERGE due to its ability to manipulate the mesh and to have that adjust itself throughout the simulation in a reasonable time. Tank sloshing type of simulations utilizing CONVERGE's adaptive mesh refinement to preferentially refine along the interface. Nozzle flow in order to consider the high density gradients across the shock and to use adaptive mesh refinement to resolve those efficiently. And lastly, turbo machinery, for example, this cavitating LOX turbo pump used in a liquid rocket combustor oxidizer line. External arrows, another good application for CONVERGE involving the inlaid mesh together with adaptive mesh refinement. So in summary, we've reached the end of our hour here. I hope everyone enjoyed the presentation and got some sense of what different models are capable of in CONVERGE for modeling the different stages of the extreme environments encountered in liquid rocket engines. I hope that you got some sense of all of the features offered by CONVERGE and how they could benefit your work. There is continuous effort underway to further validate and improve the features offered by CONVERGE, and there's many new models currently in development to be employed in this area. And with that, I'd like to thank everybody for attending, and this part of the webinar is concluded.